So in example 1, we want to verify solutions of a differential equation. We want to show that every member of the family of functions of y is equal to 1 plus ce to the t divided by 1 minus ce to the t is a solution of the differential equation y prime, which is equal to 1/2 times y squared minus 1. Now the first thing we want to do is let's find out what is the derivative of this function. So we're going to use the quotient rule. So we're going to take low times the derivative of the high minus the high times the derivative of the low divided by the low squared. So we're going to distribute in the numerator to get ce to the t minus c squared e to the 2t. And then we're also going to distribute the negative ce to the t. So we get plus ce to the t plus c squared e to the 2t. And so what's going to happen here is when we combine like terms, we're going to end up eliminating the squares. And so then what we end up getting is 2ce to the t power divided by 1 minus ce to the t squared. Now what we want to do is, in order to check and see if it's a solution, we're going to use the differential equation that was given in the problem. And the differential equation that was given in the problem is y prime, which is equal to 1/2 times y squared minus 1. Where from initially we know that y was equal to 1 plus ce to the t power divided by 1 minus ce to the t power squared. So we're going to substitute y squared then to be this following substitution. So what we're doing is that we're substituting this now in for the y squared. And so now what we're going to do is we're now going to go ahead and then separate the numerator and denominator. So we have 1 plus ce to the t squared divided by the quantity 1 minus ce to the t squared. And we want to subtract 1. Well, we know 1 can be any fraction, and so we have to find a common denominator. So if this is the denominator, then it also has to be the same thing as the numerator. So now we can subtract these two fractions. So now we have a common denominator, and now we're going to go ahead and square the first binomial and then subtract the square of the second binomial. So if we multiply them out, this is a perfect square trinomial. So we end up with 1 plus 2 times ce to the t plus c squared e to the 2t minus 1 minus 2ce to the t plus c squared e to the 2t. Now once we distribute that minus sign, then what happens is that we can eliminate the ones because they're opposite, and we can eliminate the squares. So we end up with 4ce to the t divided by the denominator 1 minus ce to the t squared. And now if we simplify the 4 and 2, what we end up getting is 2ce to the t divided by 1 minus ce to the t squared, which is what the derivative was of that function. So we verified that it was a solution to that differential equation. So we can say that every value of c, the given function, is a solution of the differential equation. So that means no matter what you choose for c, it's going to be a solution to that differential equation. And what that means here is if you look at the graph of figure 5, it shows graphs of 7 members of the family in example 1. The differential equation shows that if y is approximately plus or minus 1, then the derivative is approximately 0. And that is borne out by the flatness of the graphs near y is equal to 1 and y is equal to negative 1.